Good morning, General Chemistry. How are you today? Can you believe it? I can hardly believe it, but we are actually on our last topic of our semester, and that is gas laws. Whew. It's been a rocky road this semester. Lots of changes, huh? I hope everybody's doing well. We're going to have a couple videos in this gas law section. And I want to start this first video kind of like we've just done with our thermochemistry. I want to start it with a whole lot of defining and some of the basics and the vocab. We'll do a couple little sample problems, but then our next two videos will be just calculate. So let's start this one with, why do we give a crap? Right? Why do we even have gases separate? Why is this a unit at the end of the semester? Why don't we just tackle everything all at once with our chemistry? Well, I want to actually start with water, and I want to give an example. If we picture water and we think about water in terms of density in its three states. So we've got solids, we've got liquids, and we've got gases and gas. Okay, so we've got steam, we've got regular water as we see it, room temperature, and then we've got ice. So I just want to write out the density of water. It sounds silly, but remember, density is a measure of how much stuff in how much space. So if I write out the density of water as a solid, that would be your ice cubes. It's actually less than 1. This would be why your ice cubes float in your water. Okay, water is a strange entity. It's its own being. So most of our elements and most of our molecules, our solids, are more dense than our liquids, except water. Our ice cubes float. They don't sink. Okay, then just your glass of water at room temperature, that is actually awful darn close to 1 gram in a milliliter. And then if we look at our gases, holy crap, stop me with the zeros. Look at that. If you remember back to our first sections in class on math and numbers, this is actually 3 orders of magnitude different, or 1,000 times different than our densities of our solids and liquids. And if you look at our solids and liquids, they're actually pretty similar. Yeah, they're different just enough for ice cubes to float, but those numbers are fairly similar. Our steam, however, drastically different. Okay, what does that mean and why do we care? It means we're going to have some different properties. So I'm going to list out, there's lots of properties, but I want to list out some of the ones that we're going to see in our gas laws. All right, so one of our first properties is that our solids and liquids, they do something called hold their shape. All right, and you're thinking, no, dude, when I spill my coffee, it goes everywhere. Well, it does, but it still stays within the shape of a puddle, okay? It still stays within a shape. All right, the difference between that and a gas is that a gas will completely fill any container. Okay, so if you're in the classroom and you spill your coffee, you're going to have a distinct puddle on the floor. If you go and you buy some really awful perfume and you walk in the classroom, the second you hit the classroom, if you shut the door behind you, within a matter of seconds, the entire classroom will be filled with that god-awful perfume smell. You know what I mean? You ever walk behind someone or you hop in the elevator and someone's got perfume on that's not quite your favorite and you can't get away from it? That's what I mean by fill any container. Gases literally fill their containers. And why is that? There's just a whole lot more kinetic energy here. You've got a lot less stuff. You've got a lot more freedom. Those gas molecules are moving so fast. And of course, they're at a higher temperature in the case of steam, but that doesn't have to be the case in other gases that are gases at room temperature. But we've got a lot more kinetic energy and a lot more freedom. So those gases will fill any container. All right, holy crap. So that means right away that we're going to be super conscious of our container. So when we think about gases, we're going to always include the container. We need to have information on the container. You can have a little bit of gas in a huge container, or you can have a lot of gas in a little container. And that is leading into another property. You cannot compress our solids and liquids, but you can compress a gas. All right, you see that when you buy a tank of balloons, you see that in the tires in your car, you see that all over the place. You can take a balloon, blow up a balloon, take your hands and squish it. You can compress it. You can go from carbon dioxide gas, you can squish it and you make carbon dioxide as dry ice. You can compress gases. So in order to really think about that, because you can have a different size container and different amounts of gases in there, we have to consider pressure. Okay, remember we defined pressure earlier this semester. When you have something like a container, you have a balloon, and you've got, let's tie off our balloon. What is giving it that shape are those little gas molecules smacking on the side of that balloon, on the inside and the outside. And that kinetic energy is our pressure. So with gases, we have to consider always volume and pressure. And then as we work our way through our properties, you can see that they're quite different. So we have to really think about some of these properties. This is why our gases, we're going to treat them separate. We have to include lots of variables with our gases that we don't always include with our solids and our liquids. They will also completely mix. So it's possible to have mixtures of gases and you don't need to stir them. They're going to stir themselves. Again, it's all that kinetic energy. They're smacking around, bumping into each other. They stir themselves. So you can have 2, 3, 4 different gases. Like when you blow up a balloon, you've got several types of gas in there, and they will be thoroughly mixed. You don't need to stick a stir bar in your balloon. They're going to completely mix. Okay. And then, of course, because of this kinetic energy, we're going to keep in mind temperature. Temperature is going to be a big factor. We're going to see that in some of our laws. So we have to keep in mind temperature because that's going to change that kinetic energy of those gases. And then, of course, we never forget moles. So we're going to consider moles. We have moles on both sides here. Our moles are going to end up being a big factor in our gases. So because of these total different properties, we have to actually treat gases different in chemistry, in our math, in our calculations. Even when it comes to our moles, we're going to have a different set of equations because we have to keep in mind all of these variables when we're looking at our gases. Okay. And we don't always have to, we still keep it in mind with solids and liquids, but it doesn't change the whole dynamic of your system. Well, I can't really say that, I guess. You can take a liquid and vaporize it. You can really still change the dynamic of your reaction, and we'll learn that in kinetics and in equilibrium and all kinds of situations in Chem 2. But for our gases, it has to be known immediately in your problem because it's going to tell us how much gas we even have in what kind of situation. So we're going to keep in mind those property differences. So every time we deal with our gases, we're going to think about those variables. So our gases actually have been a study for, almost 400 years on our gases. We're going to start all the way back with Boyle's. If you remember, we heard about Robert Boyle back on our first day together. We talked about that transition from alchemy to chemistry. And a lot of chemists and physicists look at the work of Robert Boyle in his book, The Skeptical Chemist, and I'm going to spell it the way we would spell it, but I believe it was spelled a little bit different back then. But his book, The Skeptical Chemist, was the first transition from looking at chemistry as just a mystery and magic to looking at trying to study those systems using a very specific experiment and making small changes and studying what happens. And Robert Boyle did that with gases. Now, in this video, I've got an absolute million links. So there's so much out there on the gas laws because they've been known forever. So I put some links for each one of these headings that are just sort of background info in case you didn't get a textbook or anything. These are just some open areas. And then Boyle's Law itself, it's really fun to just see this in action. So I put a couple quick videos. I'm sure you can find a million of them on YouTube, but here's a couple that are fun for Boyle's Law. And then I'm going to refer to a little bit of that math, and we're going to just draw a little bitty graph of Boyle's Law. So if you want to see the math behind that and what that graph looks like, here's a link for that as well. All right, so what did Boyle actually look at, and what did he discover in looking at his gases? So what he did was start with a system, and we just learned that term in our last set of videos. So he started, let's start generic. Let's just say he took a balloon, he tied off that balloon, and now we learned in our last set of videos, this is now a closed system. All right, it is full of gas. You've got all kinds of gas molecules in here. Full of gas. We've got gas molecules exerting pressure on the outside. That's what's giving that balloon that shape. So if you take that balloon and you seal that system, so you're sealing the amount that is in that balloon. So that means your moles in that balloon are constant. And now you're doing that out in room temperature in your kitchen. You are keeping your temperature constant. So what he did then was consider that size or volume of that balloon and how it changed with pressure. So he took two different variables and he made small changes and he recorded them. And he actually got to a place where he could plot it. And what he noticed first was a nice curve. And then in order to actually get a linear plot, he needed to involve a constant. So the actual relationship that he saw, and I'm going to give you the equations here in a second. So he plotted pressure. The only way to get this then linear is he had to invert that volume and use a constant. And why did he care about a linear plot? Well, that's giving us the relationship between pressure and volume. And the equation he saw, and in this study that he saw that his pressure was actually inversely proportional to volume. That's how he could get that linear plot, and vice versa. Volume is inversely proportional to pressure. Okay, now what does that mean? That means that as you increase your pressure, you're going to decrease your volume. And vice versa, if you decrease your pressure, you're going to increase your volume. Okay, you can see that just simply. You take a balloon between your hands and you start to squish it. Your volume just went down and you applied pressure. So watch some of those videos on the demos. That'll just sink in your mind on what that means. And then how did he get that math to work? Well, he had to multiply pressure times volume and use a constant. And he was able to get that linear plot. And then he ended up writing out an equation. Okay. Oh, I just wrote the same thing. Well, that's redundant. Okay. So he ended up writing an equation that if he kept the system the same, so he used the same balloon, same system, he literally took this balloon up here and made small changes in the pressure and the volume, but he kept the same closed system, so that meant his moles stayed the same, and then he adjusted and kept the temperature the same, then he had a direct relationship where he could take that first set of conditions for his balloon and then he could jack with it. And this is our famous Boyle's law. If you've had any of your bio already and you've learned respiration, if you're scuba diver, any of this is Boyle's law. Okay. And why is Boyle's law so important that way? And why do we even think about that for our lungs or for different situations? Well, let's draw some really, really bad drawings and try to, let me insert a page here. I need my keyboard up. All right, so let's give ourselves just a little bit more space. And now for Boyle's law, why do we even consider that in so many places like scuba diving? Okay, let's start with just basic snorkeling. And let's draw a nice little picture. Oh, look at me, I'm swimming. I've got my little feet out here. I've got my hands out here. And I'm swimming. And really, I am just one big set of lungs. So let's draw our lungs in there. That's probably the worst drawing in America on lungs, so I guess that's why we label it. All right, I'm one massive set of lungs, and I'm floating along the water, but I really just want to check out this little starfish down here. Wow, that's a good drawing. Okay, let's skip that. Let's go for that shark. Let's go for a cute little fish. We see this cute little fish down here. It's got lips and it's got some massive fins, and you're like, wow, I've never seen an ugly fish like that before. I have got to check it out. So what do? You take a deep breath, you hold your breath, and you dive down. Now it turns out that for every 33 feet of water, you have a full atmosphere of pressure being applied. So if your little fish is 33 feet down and you hold your breath to go see it, what did you just do? You closed your system. All right, now Boyle's law applies. So the size of your lungs, let's kind of draw a little schematic. Boy, that looks like a tooth, doesn't it? All right, so let's take your lungs. When you're up in just one atmosphere swimming, and you now went down 33 feet, what just happened to the volume? You doubled your pressure. You just went half your volume in your lungs. So this would now be at 2 atmospheres. This would now be half your volume. And you feel it, don't you? If you go swimming and you dive under the water, what do you feel? You feel that pressure. You feel all those water molecules smacking on you. You feel it in your sinus cavities because those now are a closed system. You feel it in all parts of your body. You feel that pressure. But what's okay about this is you have your closed system. It is still closed. And then what do? You get a little tired and you cruise right back up to the surface. So now what happens? Your lungs go right back to normal. All right, so if you're snorkeling, that's fine. You've just shrunk your lungs, but now they just went back to normal. What makes scuba not fine is that if you are now swimming on the surface, let's put a tank here, okay? I've got a mask. You still have a snorkel just hanging when you're on scuba. You've got a big scuba tank. And you've got fins now because you're a rock star and you're going to dive deep. So you've got your little fins. And then, of course, you're still one big set of lungs. Okay, but now you're breathing in from that tank. So when you dive down that 33 feet and you are breathing in on the tank, you do not have a closed system. Your lungs are normal size. Okay, but now, sweet Jesus, you're out snorkeling and you see the hugest, nastiest, oh my God, are those teeth one of those really ugly deep sea ocean fish? And I mean, for a minute, you're startled. Well, what do you do when you get scared? You hold your breath. Well, now, holy crap, your lungs are normal size down here. You hold your breath, you freak out, and you go back up to the surface. What did you just do to the size of your lungs? Holy crap, you doubled them. And now, do you even have enough space in your chest cavity to hold that? No. So what's the number one rule of scuba that you never, ever forget? Even if you're out in another country drinking shots of tequila and somebody offers to take you scuba diving for $20, even though you're not certified, don't do it. But if you feel like that's a super good idea, the number one rule to scuba is that you never, ever stop breathing. And why is that? That is Boyle's law. Okay, you're going to really mess up yourself if you do that. Okay, thanks for letting me draw. Awful. Isn't that great? All right, so let's move on then. Let's tackle our next law. Okay, so far we've got Boyle's law. And if we have our same system, we can use this equation. But remember, this equation is only valid if our moles stay the same. So when you hold your breath in your lungs, you're not adding or subtracting any moles in your lungs. That is constant. And you're in your body. So that body temperature is pretty consistent. So that's why Boyle's law works, is that you can do both of those and keep them straight. All right, so let's do one little quick math problem then. So what if you have a tank of gas and it contains 1 liter of gas and you are at a pressure of 165 atmospheres, and you take that same tank and what you really need is a pressure of 1.1 atmospheres. So you have drastically changed the pressure in that tank. What would be your new volume? All right, for all of our gas laws, there's only 2 ways to jack with you. Number 1, funny wording. Number 2, unit conversions. So I solve them the same way each time. I take whatever is given and I spell it out right underneath my gas law. So I'm going to take that first volume is the 1 liter. And that first pressure is the 165. All right, then I'm going to take, okay, what am I given? I'm given a second pressure. Oh, let's write it down here. Let's match. We're given a second pressure. And then what's the one that's missing? Always in gas laws, there'll be one missing. That's the one you solve for. So then you do a little bit of algebra and you take your equation and you rearrange for the one you're trying to solve for. So we're going to take P1V1 over P2 and solve for that V2. So let's put in some math and let's see what we get. So I'm going to plug in that 165 atmospheres and that 1 liter. Oh, that looked like a K, didn't it? And then our 1.1 atmospheres, that new pressure underneath, and literally plug and chug on your calculator. Grab your calculator and you're going to get 1650 for that new volume. And now look at our units. They line up so nice. You just cancel it and you're left with the unit of volume. All right, way back in the very beginning of class, I handed out the unit conversion sheet. I handed out that old conversion sheet for a very specific reason. All of your units are organized by type. So you have pressure and volume in different little cubes on that unit conversions. That will be really helpful for the gas laws. So you can keep in mind those units. And we'll talk about units in a little bit. Okay, how fun. All right, so next, our Boyle's Law was in the 1600s. So let's put a year on that one. Okay, our Boyle's Law, oops, somehow I can't move. There we go. Boyle's Law, 1661, when his book came out. He started studying his gas laws a little bit before that. That is when the actual book came out that then he wrote The Skeptical Chemist. So that is staggering, right? All right, Charles then was a physicist and a chemist about 100 years later. This is now in the 1780s. And he noticed something in Boyle's work, that there was actually some discrepancies in his data. Something funky was happening when the temperature changed. Sorry, I just hit my coffee there. All right, so now let's switch into 100 plus years later. Let's look at Charles' Law. He literally looked at the work of Boyle's and said, well, wait a second. What about temperature? What is temperature going to do to this whole system of balloons and gases? And so Charles set out to literally study that situation. Okay, well, what would happen if you jack with the temperature? And he wanted to keep along the similar lines of, okay, let's keep some things constant and let's only mess with two of those variables so we can see what their relationship was. So he looked at the relationship of volume and temperature, not just volume and pressure. So this is kind of fun. What he discovered, and he did the same thing Boyle's did. He took a system, he kept his system the same. So let's tie off our little balloon, closed system. So now what is the same for him? Again, he kept his moles the same. And then he kept a standard pressure. And what he did was take that little balloon and change the temperature and then record the volume. So he found that same curved plot, just like Boyle's did. He did a little bit of manipulating, and he ended up finding that he had a direct relationship between volume and temperature. But in order to do that, he needed a constant as well. So what he found was that volume is equal to a constant times temperature. So this is pretty awesome. That means that volume is proportional to temperature and vice versa. They are proportional to each other. Okay. And this is brilliant because now if you keep your system the same, he also had an equation. So let's write out Charles' Law. So he kept things constant. He kept his moles and his pressure constant. And then he observed that direct relationship between volume and temperature. So this is pretty cool. You guys see this in everyday life as well. If you are feeling real sassy and you want that beer cold, you throw it in the freezer. Only then your friends come over. Well, not now because you're social distancing, but someday your friends come over and you get chit-chatting and you start telling them about all the cool stuff you're learning in Gen Chem. And then it takes over, and before you know it, you forgot that can of beer in the freezer. And you go back to get it the next day and it exploded on you. Oh, and then if you're from Wisconsin like I am, that happens in your car when you forget to unload your 6-pack of sodas at night. You come back the next day and they've exploded all over your car. That's super fun. I think everybody from Wisconsin's done that at least once in the cold states. You start jacking with your volume and your temperature, and you literally, if your container is somewhat rigid, you can blow that sucker. So on Charles, even if you don't look at any of these tabs, if they're not fun for you and you're freaking out, and we only have 1 week left in this semester, watch these videos, okay? This is going to demonstrate Charles' Law. So there's a couple of them. They're pretty corny, but they're fun. And if you've got kids, they'll probably like to watch those too. And then you take it the next step and you go a little bit bigger. Okay, this is one of my all-time favorite videos because it's so wrong. There's just really a lack of safety in this one. So watch this video and imagine you're in class with me and we are picking on the safety part of this video. And then even better, go huge. All right, let me just give you a hint. You're driving down Mopac and you look over and you see that train going down the middle tracks. Do you ever wonder what happens in those tanks if all of a sudden the weather changes and now you've got a big tanker car, but your temperature just dropped 40 degrees? What do you think is going to happen? Okay, now of course they have a relief valve. So you have to make sure your system isn't completely closed. So they can have some safety measures now, but watch that video. It's actually pretty cool. All right, so then our Charles law has that nice relationship between volume and temperature. There you go. All right, so as your volume increases, your temperature increases. They are proportional. And vice versa. You raise the temperature or lower the temperature, and you are going to lower the volume on your system. So that's pretty fun. Let's put that into some math. So let's say we take a balloon, and our balloon size is 2.0 or 2.80 liters. And we actually then throw it, and we've got it in ice. Okay. And then we actually really need to get to a volume of 2.57 liters. What temperature are we going to have to go to get that to work? Well, bust out your calculator. Let's do this. All right, let's do my same trick. Let's list out our variables. It sounds silly, but as we get wacky wording and lots of unit conversions, it's going to be helpful. So our first volume is 2.80 liters. Our first temperature is 0 degrees Celsius. Okay, our first volume is 2.57 liters. And then we want to know our second temperature. Okay, so what are we going to solve for then? Well, we need to take our equation and rearrange it because we need to solve for T2. So let's take our equation then, and let's do some rearranging. So what I'm going to do is, I guess, multiply my T2. I'll do this just once, and then the rest of our gas laws, I'll just give it away for free. So let's take our T2 and put it up here. And then let's go ahead and rearrange again and end up with our T2, V2, T1, all over V1. All right, so let's plug and chug our numbers in then. What's our V2? 2.57 liters. Okay, what's our T1? 0 degrees Celsius. Okay, what is our V1? 2.80 liters. And grab your calculator. I'm going to grab my calculator. And what do we get for that then? You get 0. Well, what? Okay, so in our gas laws, we don't use Celsius. Okay, we have to do a unit conversion. What? Into Kelvin. In our gas laws, we always use Kelvin in our temperature. And you've got this on your unit conversions table. We add 273. So how do we convert that? That is going to be 273 Kelvin. Ooh, let's try that again. Okay. 2.57 times 273 divided by 2.80. So that's going to give us 250.6 Kelvin as our temperature. Now, of course, if you want to convert that to Celsius, you can. I'm going to subtract that 273, and we're going to get to a minus 22.4 degrees Celsius. But the trick with gas laws is that you have to use absolute temperature, and that is Kelvin. You can't use Celsius or Fahrenheit. We've got to use our Kelvin. So get ready to unit convert, because every time we see a temperature, we are going to convert it to Kelvin. Awesome. All right, let's fast forward. Now, Avogadros we tackled a little bit already in class, so let's fast forward to the 1800s. I love it. I love it. So we're now in the 1860s, I believe, for Avogadro. And we kind of drew this out in class. And, or actually, I guess it was on a video, wasn't it? We only ended with our Unit 2 before spring break. So in our video, what we looked at was Avogadro's really shocking idea at the time of, okay, we're doing all these gas laws. We're putting gases in balloons. And we are noticing that we have to keep in mind volume, pressure, and now temperature. And then he tackled moles. So Boyle's was pressure and Charles was temperature. So now Avogadro was moles in relation to volume. And his idea was that if you've got two balloons that are exactly the same size, okay, so if we have the same volume there, then that has to come from the same pressure. And the pressure is literally those collisions of molecules, no matter what they are, and that is our moles. And so it gave us a way to count those particles. Of course, his ideas weren't accepted until after he died, but we see them today. So he actually gave us 2, 3, 4 really important ideas. The first one was that in gas laws data, he did the same thing Boyle's and Charles did, and he looked at volume, this time versus moles. So in order to make that happen, he had to have a constant temperature and pressure. Okay. He also could get to a linear plot if he used a constant. So his equation looked similar to Charles' law. And it turns out that volume is then proportional to moles and vice versa. Your moles are proportional to volume. So if you increase your moles, you're going to increase your volume. And that kind of makes sense, right? You put more stuff in. If you blow in more in your balloon's going to get bigger. Okay, and then same thing for subtract. You remove some moles, you decrease your moles, you're going to decrease your volume. So there is an Avogadro's law, and it looks very similar to Charles' law. Okay, and what's awesome though with Avogadro is that we still have this same idea where we're keeping some things separate. We've got a constant and we've got volume proportional to moles. But what he had was this really exciting idea that has helped us a whole lot in chemistry, is that it actually just depends on the collisions in those molecules. It doesn't matter what the molecule is. So it could actually be any molecules or any gas. Okay, now this is mind-blowing, because you could have CO2, you could have hydrogen. They're different molecules. They weigh different. Why aren't they different? But in this case, in these gases, they acted the same. So he gave us a shortcut. Whoa, everything disappeared there. Hang on, I think I hit something. All right, so he actually gave us a really important shortcut. Are you ready? All right, that shortcut is that at STP, that is standard, not the band. I don't think you guys are old enough for the band. At standard temperature and pressure, isn't that what he kept constant right there in his equation? At standard temperature and pressure, it doesn't matter what the gas. If you fill a balloon to 22.4 liters in volume. That is 1 mole. Oh, shut the front door and write that down. That feels like a very good unit conversion. So you can have 1 mole of any gas. And if your balloon is 22.4 liters, you have 1 mole. This is so important. But it has to be at STP. And our standard temperature and pressure is set here. And our standard temperature and pressure is actually going to be 0 degrees Celsius or 273 Kelvin and 1 atmosphere in pressure. That's temperature, not pressure. Okay. So put a box around that because we are going to use this unit conversion, but only if we're at 0 degrees and 273 Kelvin and 1 atmosphere of pressure. This is not valid if we're at different temperatures and pressures. Okay, now that doesn't mean we're screwed if we're not at STP. It just means we're going to use a different equation. So this is awesome. So these are our relationships so far, and we just got to a magical place where if you look at it, didn't we just relate volume and pressure, and then we related volume and temperature, and then we related volume and moles, and all of them had a constant. Do you notice I didn't give a number for this constant? No need, because if we combine all of these terms, we are going to combine into something called the ideal gas law. You can always use the ideal gas law. We don't have to use separate Avogadros, Boyles, Charles. All of those, you have to keep things constant or be at STP. Well, normal chemistry isn't always something constant, and you're not always at STP. So that's actually really useful in a very closed system if you've got a balloon in a bell jar. But what if you're out in real life and you're looking at a car tire, or you're doing a reaction in the lab and the temperature keeps changing? I mean, there's all kinds of reasons why you wouldn't have something constant. Look at our combustion reactions from our thermo unit. Nothing was constant in there. Your temperature changes, your amounts change. All kinds of things don't have to stay constant. So let's combine everything. Let's combine the fact that we related all of our equations back to volume and that we had a constant in all of them. And then one big equation is called the ideal gas law. And we can use this in everything. The trick to our ideal gas law is that we have to keep our units straight. And let me show you why. Okay, we're going to keep pressure, but now we've got to relate pressure back to a constant. So our pressure, we're going to use atmospheres. There are several gas constants. We will use just one. If you're in physics, you use a different one, but they're all on your unit conversion sheet. Okay, let's work our way through. Our volume will be in liters. Our moles, wait for it, will be in moles. And then what is this strange R? Well, let's take our temperature first. We're going to be in Kelvin. And then R is our universal gas constant. So we have to match our units to our gas constant. There are 4 different gas constants on your unit conversion table. We will use the one that matches our units. That's going to keep everything the same. And our units, wait for it, are liters, atmospheres over mole, Kelvin. So you see how they match? Here's our units, here's our units. So you can see where we're headed. We're going to use the ideal gas law with our chemistry reactions, and we're going to do some unit conversions here with those units. We have to make sure we're following our units, or we can't use that gas constant, and we really have to use that gas constant. So where do we head from here? Our next video, we're going to take this ideal gas law and we're going to apply it. And then we're going to have a third video where we apply that in chemistry reactions. So we're going to do some chemistry with gases. But before I leave you, I really want you to check out this real life. This is a real life gas disaster. It was actually a real big mystery in the 1980s. It made the news. An entire village mysteriously died in Cameroon, Africa. And it took scientists about a month or two to figure out what happened because it was in a warm climate in Africa. And yet this entire village died almost instantaneously and their bodies had signs of frostbite. So how do you explain that? Holy crap. This is something straight out of like a Netflix movie, but it actually happened, and it happened in real life. And there are 3 lakes on the globe that villages sit next to that this disaster can happen. And so it's just really interesting. So click on it, and it'll talk about the science just a little bit. And it's a really interesting story. So you'll have to take a look at it. This is another reason why we give a crap about our gas laws. All right. I hope to see you guys soon in our next video.